All right, so let's move on to logistic growth models now and looking at the homework assignment, make sure I get through all the questions. So the first thing we ask you to do is to start with an initial population of 20 adult females, K of 100, and compute the population trajectory over 100 time steps for our max values of 0.02, 0.04, 0.08, and then plot those on the same graph. Okay. Um, so let's just take a look at the spreadsheet and see how we would do that. So here we have the equation for the logistic growth equation, and we just need to put that into this first cell here. So we always start with an equal sign for every good equation in Excel. So we want to start with n sub t, and then we're going to multiply that times, in parens, 1 plus our value of little r. Whoops. Oh, I didn't like that. I put an underline instead of a plus. Let me do that again. Hit the wrong key. 1 plus. And now we want to take little r, and we want that to be an absolute reference. So I'm just going to hit F4, and then I'm going to multiply that times, I always forget, 1 minus, and then we have our equation for how little r declines as n increases. So again, we want to use previous time step value of n. We divide that by our carrying capacity, and again we want that to stay the same, so we're going to make that an absolute reference. Now we need to close all these parens, and the cool thing in Excel is it'll highlight those parens that it's matched with as you add them, so I can see now that I've got all three. It doesn't like it if it doesn't have closed parens. And this is looking about right. When we use the exponential growth equation, this was 20.4, but we're partway into our population growth trajectory here for the logistic, and so it makes sense that it slowed down a little bit. Once we got that, all we have to do is copy it down to 100, and bingo, presto changeo, it's plotting the population size over time. One cool thing you can always do to make sure you're plotting the right values in Excel is you just click on that line on your plot, and it'll highlight the X and Y values that you're using. Okay, that looks right. And just hit escape. And now to do this for a value of little r of 0.04, I'm just going to copy this one cell over. Then I'm going to make some changes to make sure that it's using the right values. So now we want to use a little r of 0.04, which is in C13. Okay, we could leave that value of k to be the same, or we can change it. And now you see it's growing a little bit faster. We copy that down, and bingo. Now it's giving us our second logistic growth equation for those same parameters, except that our max is 0.04, and I'll leave it to you to do the third one. Then there's a question in your homework about comparing those to the exponential growth. You've already got all that. I'll let you work through that. Now we ask you to do some plots for n sub t plus 1 minus n sub t. Remember, that's just our delta n, okay? Change in population size from one time step to the next. We talked a lot about this when we were talking about the harvest models and maximizing the rate of harvest from a population. And then the other thing we want you to do is to plot the per capita growth rate, and that would just be delta n, so n sub t plus 1 minus n sub t divided by n sub t, okay? And we want n sub t on the x-axis for both of those. So again, pretty simple to set that up in Excel. To get n sub t plus 1 minus n sub t, it's just simply taking the population size in the next time step minus population size in this time step. So that's our change in population size, pretty small, 0.32 individuals here, okay? Oh, and I'm doing it for little r of 0.02. In the homework assignment says you can use either 0.02 to 0.04 to 0.08. Probably best to stick with 0.02 or 0.04, okay? Once you've got that equation for a change in population size, you can copy that down to 99. If you go to 100, you'll see you'll get this strange value, and that's because it's saying take what's in, the next time step and divide it by the number in this time step. We don't have a population estimate for the next time step, so we can just stop it there. And when we do that, look, it actually plots our delta n versus population size, and you're getting that familiar hump-shaped curve with a maximum at about 50. The reason it's not going all the way down here is because we started at 20, and because of the slow growth at little r equal 0.02, it's only gotten up to 64, but still gives us what we're looking for. And now for the per capita growth rate, you would just take that delta n and divide it by n, the number in the population at that time step. Copy that down, and bingo, it's going to plot it for you, and you should see that familiar linear decline in your per capita growth rate. Okay, so next in your homework we ask you to do some stochastic plots with the logistic growth equation. So we want you to plot 3 different values. Well, first we just want you to calculate some random values of r using a CV of r of 2, and it'll calculate the standard deviation of r for you. And once you do that, if you hit F9 over and over like we said before, it'll just recalculate all those random numbers so you can see how that changes. You can then look at some questions that we have here. We want you to hand in a graph using 3 different values of CV R max, but the same value of the R max, and ask how do those trajectories differ. And then finally we want you to put on the same graph a deterministic plot of the logistic growth function and a stochastic plot to see how those differ. And so we're asking you for 3 different values of CVR max, but the same mean. Okay, so let's go to our template and see how we do that. First thing we have to do is calculate our random value for R. Okay, so we're going to do the norm.inv function. And the first thing we have to give it is the random number, and then tell it what the mean is going to be. So we refer to our, when we really just have one value of R max here, we want that to be a absolute reference, and our standard deviation of R, again, we want that to stay pointing at that cell as we copy it down. We copy this down to 100. If we want to make sure that this is giving us a average of about 0.4 for little r, we can do that. Yep, looks like it's right. Get some negatives, some positives. So now we have to put our equation for the logistic growth equation in here. So the first thing we do is refer to population size at our previous time step, multiply that times 1 plus, and now we want to put another, now we refer to our value of little r that we've calculated, the random values, not the fixed value. And now we multiply that times parens 1 minus, another parens value in the previous time step divided by k. And again, this is the only value that we want to stay constant as we copy this down. So now I got to make sure my parens match. 1, 2, 3. That looks right. Bingo. I hit enter. And notice it drops a little. That's because my first value of r is negative, little r. So now all I have to do is copy that down. And bingo. That will give me my stochastic realization. And here's the first one here. And you can see it's bouncing up and down a little bit. Then something else to show you. Again, I've already set this up for you. What I did, we said we wanted to use different CVs. So I've identified the CVs of R that we want to use. And I just calculated the standard deviation associated with those CVs. You essentially just take the value for the CV that we include here, which is 4, and we multiply it times our growth rate, which is 0.04, to give us our standard deviation. And as we mentioned in the overview, the way we would normally view this is as a percentage. So this would be like a CV of 400%. We just use 4 here because that's a formula for converting CV to standard deviation. So let's see, I'll let you do that for the next 2 simulations. So we'll want you to turn in this plot with 3 simulated values or simulated trajectories under the logistic growth equation. And then finally, the last thing that we ask you to do is to provide a graph which gives the deterministic plot for the logistic growth curve using a little r of 0.04. And then you can use one of these stochastic trajectories that you plot here, and you want to put that right on top of, in the same graph so that you can compare the two. Okay, so that should do it, folks. Hopefully this will go pretty easy, and when you're done, you'll have lots of skills in Excel that you can use in a lot of other situations.